We're now ready to look at our second conic section, the ellipse. And I hope you took a little bit of time to preview and fill out some of the information on the front of this paper. Working backwards, you may have filled out these formulas already. We will make sense of all the letters. How about this diagram? Pretty important diagram to start getting some knowledge of ellipses. You got a center. Now, there's actually two foci on an ellipse. And yes, we do pronounce that foci, at least in math class. I know your science teachers like to call it foci. Both of them are actually appropriate. And then there's two vertices, and I mark those with V's. Now, the definition of an ellipse is that it is the set of all points xy in a plane, the sum of whose distance from two distinct points, the foci, is constant. Say what? Well, actually, an ellipse, sometimes we forget that it really is these points. It's the points that are actually on the graph. But it says that these points, they're not the same distance from a foci, but it says that the sum of these distances are constant. Let's take a distance from this point to a foci, and let's call it D1. And let's take a distance to the other foci, and we'll call that D2. Now, again, the definition doesn't say that those two distances are equal. They don't even look like they're equal. But it says that the sum of those distances will be the same. It will be constant. And what that means is, as I move this point, which is what happens as I move this point around this ellipse, of course, these diagonal distances are going to move, and they're going to change, but the sum of them are going to stay the same. Take a look at this quick video about how this definition can be used to create an ellipse. Now, to add one more thing to that video would be the question, what would happen if the foci move? What would happen if the distance from the foci to the center maybe get closer? Now, can you imagine the string that would be moving around? Those two distances would actually become almost equal. In other words, we would be drawing a shape that is more circular. So as the foci get closer to the center, it's more circular. And can you imagine if the foci go out towards the vertices, as you rotate around with your string, those two distances would be much different, meaning that you would end up with a ellipse that's more elliptical. We actually call that concept eccentricity, and at the end of this lesson, we'll learn how to find eccentricity as a number, maybe as you also studied in your physics class with planets and their orbits. Well, two more things. The major axis, as it's been identified here. Now, the major axis is always between the vertices, and it's also the longest axis. And then you have the minor axis, which is the shorter axis. Let's go over to this other diagram, and all right, so let's take a closer look at the relationship between some of these points. Now, we're going to call this distance right here from the center of the circle to a vertex. We're going to call that A. That's going to be the distance from the center to a vertex. Now, we're going to call this distance here from the center to a point on the minor axis. We're going to call that B. And by the way, this point right here on the minor axis, it actually doesn't have a name. I know, it's so sad. It's the nameless point. Maybe you can name it, but for now we'll just say it's a point on the minor axis. And then we're going to call this distance from the center to a foci, we're going to call that C. Now, the whole point behind this little discussion is trying to find the relationship between A, B, and C. Now, I know you've heard of these letters before, but how do they relate in an ellipse? Well, quickly we're able to determine that this distance right here is the hypotenuse of a right triangle involving B and C. I don't want to get another variable involved in this discussion, so I'm going to go ahead and call this right now. I'm just going to call this b squared plus c squared. Excuse me, the square root of b squared plus c squared. And again, that comes from the Pythagorean theorem in that triangle. Well, it then would reason to say that this distance, this diagonal, would also be the square root of b squared plus c squared. Now, we're going to do something a little fancy. It's going to be a little visual, but see if you can follow. We're going to take this point that has no name, and we're going to drag it over here. We're going to drag it over here to this vertex. And as we drag it, it's going to take with it this diagonal distance, and it's going to take with it this diagonal distance. And now, where are the diagonal distances lying? Well, do you see how the blue diagonal distance would have to be lying here? Do you see how the purple diagonal distance would have to be lying here? And we're about ready to make a statement about the whole length of the major axis. Okay, there's one more thing that we need to do. We need to agree that this blue diagonal distance, which is now laying on the major axis, could also be equivalent to this distance here. And so I am going to erase it over here so that we now have a full stretch of the major axis. Now, a full stretch of the major axis would have to be 2a's. Indeed, it would have to be 2a's. But it would also be, do you see? It would also be 2 square roots, because one of the square roots is lying right here, and the other square root is lying here. And even though I know they look like they're two different lengths, they're both equal to the square root of b squared plus c squared. So we're ready to make our statement. That is that 2a, in other words, the whole length, is equal to 2 square roots of b squared plus c squared. Theoretically, this would be true. And if we do a little simple math, we can cross out the 2's, and we can actually square away the square root, and we end up with a statement that you will come to know that says that a squared, or it says that b squared plus c squared is equal to a squared. We usually write it in that order. So b squared plus c squared equals a squared. Now, you can rewind the video if you need to, but you'll find out that we will use this formula often when we try to relate these three distances. And those distances, as you can see, start to show up in our formula. Why don't we take a little closer look at our formula, because it uses some of these letters. Did you catch what I did with the letter A? The letter A is the distance from the center to a vertex. It's the distance from the center to a vertex, which means that 2a would have to equal the major axis. Yeah, I didn't give you a lot of space there. Sorry about that. So 2a would be the major axis. Now, b is the distance from the center to a point that's on the minor axis. I should have had that word minor axis there, but what we're going to say is that 2b is equal to the minor axis. Okay, so b is the distance to a point from the center, so 2b is the entire minor axis. And then c, well, that's going to be the distance from the center to a foci. All right, so we have these formulas, and we're ready for our final observations, and then we'll be able to use these formulas to do some math problems. I actually have these formulas written and also a diagram that you might want to grab. But I do just want to discuss with you a couple things. First of all, the formulas will always be of the form of x squared plus y squared. both divided by an a squared and a b squared. And simply since a is always your distance from center on major axis, again, a is always distance from center on major axis. That means it's the longer distance. Again, a is the longer distance. And if a is with x, well, that means you're going to have a horizontal ellipse. That's because it's going to be longer on the x-axis. But if a is with y, then your longer axis is going to be vertical. And this means that we'll have a vertically oriented ellipse. So the important thing to understand here is that a is always the longer distance. Let's flip over to the back of the paper now and see if we can apply some of these concepts about the equation of an ellipse. Now, what we want to first do is write the equation of an ellipse. This first one has foci of 0, 1 and 4, 4, 1. We also have information about the length of the major axis. You're going to find that you do want to and will want to approach these problems visually, much like we approach the parabola problems. So I'm going to encourage you to sketch what you know. It doesn't seem like you know too much, but we'll still sketch it. We've got two foci here. We can even label them on our diagram again if we want to. But here's the deal. If you have foci that are positioned in a horizontal manner, in other words, a horizontal line passes through, well, that means that this ellipse is going to be of the horizontal variety. So it looks like we know that. We can actually make a statement about that if we wish. I'm going to write down that this has a horizontal major axis. That's because, again, the foci are always on the major axis. And how about the center? We don't have the center, but it really would be the next thing that we can find, that we can figure out. Now, the center is always going to be right between. It's always going to be the midpoint of your foci. Some of you might just be able to mentally find that midpoint. I know there is a problem that's a little challenging to find, so I'm going to work out showing you how to use a midpoint concept simply from your geometry class, where you take your two x values. Now, your x values would be the foci x values, and you average them, and then you take your two y values and average them. Now, of course, those two y values are the same, but nonetheless, your midpoint is always going to be the average of your foci. So my center comes out to be, of course, 2, 1. And we can get that labeled on our diagram also. Now, at some point, you're going to come to the realization that you have to fill in to this horizontal formula. And to fill into that, there are some things that are always true. Like there's always a plus sign, and it's always equal to 1. And really, that you just need to find A and B. And A and B are not that far away from the work that we've done in this problem, because if the major axis is 6 units long, that actually means that the that 2A is equal to 6. Because remember, 2A is always the whole length of the major axis. So finding A is just a matter of understanding what we've been given. Let me kind of organize this a little bit, even though I think you can see that A is definitely going to equal 3. But yeah, we want to find A. We also want to find B. We're going to want to find the B value. And we're also going to want to find C. Now, one of these is known, and it's known from the information that we've found so far. I hope that you realize that it is the C value. You see, the C value is the distance from the center to a foci. And whether I look at this distance or the one that goes back to the first foci, we're able to deduce that C equals 2. So it looks like if we know that a equals 3 and c equals 2, we're going to be able to use this formula that says that b squared plus c squared equals a squared to find our b value. And that's exactly what we'll do. We'll plug into that formula very carefully, b squared, again, plus c squared, and that has to equal a squared. And with a little bit of simple math, we discover that b squared is equal to 5, which means that b equals the square root of 5. We don't need to use a plus or minus because the plus or minus signs are going to be taken care of with the formula. Now, remember, the formula that we're using is a horizontal ellipse, so we're just ready to plug in for h, k, a, and b. And our final answer, when you plug all that in, should look very carefully like an x minus 2, because our center was at 2. Now that's being squared. The a value we discovered is 3, and that's also always squared. It's going to have to be y minus 1. That is squared, and our b value we found out to be the square root of 5. Of course, that's squared, and it's equal to 1. And I would imagine you might be asking, well, Mr. Naylor, should I square these denominators? Yeah, but it actually is a little bit more standard to present your answer more in a factored form, meaning without actually doing the exponents. But there's absolutely nothing wrong with getting and changing this to 9 and getting and changing this to 5. So both of these formulas are acceptable for our standard form of this ellipse. Now, the only thing that I didn't do is I didn't label a vertex, like literally label the vertex on my ellipse. And I should do that because now that I know that the a value is 3, I'd be able to give the value of this point. And I'd like to see you do that, to write that as 3 units from the center to be at negative 1, 1, and 3 units from the center over here to be at 5, 1. And now we have fully analyzed this ellipse so that we can label each important point. Again, the center, the foci, and the vertex. And if you just kind of want to draw a little sketch, there's no reason to get any string out, but it does show that you've actually drawn the ellipse itself. All right, are you ready to try a problem on your own? Had you been in class, you would be, so I just want you to take your time. I hope that the first thing you do, though, is that you sketch the foci and start thinking about what else is true about this ellipse. I'll meet you back here with the answer. All right, so I hope that the first thing you did was graph your foci, and lots of conclusions can come just from that. Maybe you were led to noticing that the center would be simply the midpoint of 0, 0, and 0, 10, so that's easy to find. You also, I hope, can conclude that because your foci are vertical, that this is going to be a vertical ellipse. That simply means that the y variable is going to be with the a value when it comes to the equation. Really, a lot of this boils down to finding a, b, and c. And we just have to take what we're given and realize how that can help us to get a, b, and c. Now, c is known by this distance that is from the center to a foci. So we can quickly conclude that, simply conclude that c equals 5. It's just kind of a visual thing. That's all I would do with that. We can also do a little bit of thinking about b, since b is involved with the minor axis, in other words, that shorter distance. We can use this 4 that's given to us to say that 2b would have to equal 4. Be careful, not b equals 4, because remember, b is the distance from the center. So 2b, meaning the full distance, would have to equal 4. That means, of course, that b equals 2. So once we know that b equals 2 and c equals 5, we're going to be able to go over here and solve for a. Now remember, b squared plus c squared, b squared plus c squared equals a squared. So we want to kind of get that formula straightened out, and in this case that means that a squared is going to equal 29, which means that a equals the square root of 29. And we're ready to fill some things into our formula. Again, we're going to be using the vertical formula. That's because a, the major axis, was a vertical number, so that one will go with the a. And all I got to do is just fill in the center for h and k. Now h is actually 0, so I'm going to skip filling that in, but the b value is 2, so I can write that as 2 squared. The y value, excuse me, the k value is 5, so I can fill that in as y minus 5, and then the square root of 29 squared. And as we said before, you can write this as 4, and you can write this as 29, but it's actually a little bit more standard to see it written in the factored form. Now, don't forget that it's equal to 1. We actually didn't talk about why that's true. I'm going to save that for another conversation, but it just has to do with the relationship between the distances with our ellipse. Now, as a little bit of some extra, what I want to do is I want to talk to you about solving this equation for y. You might say, well, why do I want to do that? Well, I want you to see what the equation looks like when it's solved for y, for one thing, and it would also be something that we could put in our calculator. Now, if you solve it for y, there'd be quite a bit of undoing, but we can just kind of verbally talk about how we would undo and move this x squared over 2 squared over to the other side. So we would subtract that over. That's actually going to look like a 1 minus, I'm just going to fill this in over here because it's the space that I have. So that would look like 1 minus the x squared over 4. And then we're going to have to undo this, this denominator. We'd have to multiply that to the other side. If you multiply that to the other side, you would look like you'd be multiplying by 29. And you're only going to, well, not only, but then you're going to have to undo this square. So that's going to cause us to do a square root. We'll do a square root of both sides. Now, technically, you would get plus or minus at this time. And there is one last thing to do, and that would be to add 5. You might notice that this 5 right here would still be tagging along, and I would have to add that to the other side, actually to the outside of this equation. Now, if you would like, you can type that equation into your calculator, into your y equals screen. I probably would have done it in class, and you would have watched me do it. But what I want you to see is that that actually does produce an ellipse. It actually produces an ellipse that is centered around 0, 5, that has foci that we have marked, and you would even be able to notice these vertices. And speaking of noticing the vertices, they actually would be something that you would want to label. It would become part of like your final analysis. But now that you know that a equals the square root of 29, you would be able to simply add and subtract the square root of 29 from the center. A little strange, isn't it? But you could write your vertex at 5 minus the square root of 29. Again, the square root of 29 is that a value. And I could write this one up here as 5 plus the square root of 29, and that would give me that point. Okay, do you need to take a break yet? If you do, just push pause, but when you're ready, we're going to basically do this backwards. We're going to analyze an equation, and along with this is always the idea of drawing a sketch and coming up with all the features and values of your sketch. Now, the equation that you have here, you might say, well, it doesn't look much like an ellipse. No, that's because it doesn't have the fractions, and it's also not equal to 1, which is kind of where we start. If we just make this equal to 1, well, ta-da, we have some fractions. So we're getting closer to an ellipse. Let me help you to continue to try to think about this in standard form, meaning maybe thinking of 64 as 8 squared right now. See how we like to think of it when that's in that factored form? Of course, we can also do a little bit of a simplifying with 4 and 64 so that the denominator becomes 16. But really, we want to write that as a y squared over 4 squared. And then, of course, we have our wonderful 1. Now, all kinds of things you can figure out from this equation. People do this in different orders, but maybe you notice that since there's no h and k value, that your center would be at 0, 0. That's a fine thing to notice. I would like you to notice that the larger value is with x. Now, since the larger value is with x, this is going to end up being a horizontal. It's going to end up having a horizontal major axis. Now, since it has a horizontal major axis, that also means that that 8 is going to be our a value. Again, a is always the larger value. Now, we would have a vertical minor axis, but we can just jump down here and we can make the simple conclusion that, of course, b would have to equal 4. And as we've done many times, finding a, b, and c becomes our order of business. And for this particular problem, that really would be finding the c values so that we can find the foci. But let's work through that. Remember, the formula is b squared plus c squared, and that equals a squared. So we end up getting, with a little bit of math here, that c squared is equal to 48, and that means that c equals, of course, the square root of 48. I'd like to see you simplify that. You might as well pull a 16 out of that 48. That's going to turn into a 4 root 3. Now, that's your c value, 4 root 3. But what that does is that helps you to, that'll help us to get our foci. What I would say is that I want to make a sketch. There's a little too much going on here without seeing something. So let's get the sketch involved. Here's the center at 0, 0. The 8, remember that 8 that we found. Now, that is going to give us the distance out to a vertex. You know, you can see now that that has to be at negative 8, 0. In a similar fashion over here to the other side, we'd have to be at 8, 0. So use your sketch, make it visual so that you know that you are that you're putting your points at the right place. And what else? Well, the foci, right? The foci, we know, have to be somewhere along this major axis. You did know that, right? The foci have to be on the major axis. So, well, that's what was it? 4 root 3. Well, that's going to help us to identify those values. So we move negative 4 root 3 to the left, and we move 4 root 3 to the right, and that gives us our foci. We actually have everything that we need. You don't have to, but sometimes students like to label a point on the minor axis. We don't have a name for this point, so I really don't have to label it, but I can identify it as 0, negative 4, and 0, 4, plus that kind of helps me to have some more points when it goes to drawing that ellipse. So, standard form, right, of an ellipse. And speaking of that, that would be our order of business for this equation. What you want to do is you want to get that equation in standard form. Do you think you can do that so that we can analyze it, so that we can come up with the center, the foci, and the vertices? Well, I'll tell you what, I'm going to help you get started with turning this into standard form. But you may not be too surprised at some of the things I'm going to say. And then once I finish getting it in standard form, why don't you see if you can identify the rest of the points on the ellipse. So you're going to have to get your like variables together. And once you get those like variables together, you find out that you kind of need a place for the constant, and that constant, the place that it needs to go is over to the other side, because what's going to end up happening is both of these purple and red statements are going to be completed. We're going to complete the square. And so whenever you're ready, we're going to add in that perfect number. Over here on the purples, that perfect number that we need to add in is a 4. Of course, I have to add it to the other side also. And now there's a little bit of a middle step here with the red numbers. You'd have to factor out a 9. That way you can have space for the perfect number. And of course, that perfect number is 1. Now, remember, we didn't add 1 technically. We added 9 times 1. That means that I have to add a 9 to the other side to keep this equation balanced. All right, well, you didn't complete the square just to leave those terms the way that they are. You completed the square so you could write those terms in factored form. So x minus 2, the quantity squared. What's it going to be for the red one? Well, you keep the 9 on the outside, and you're going to write it as 9 plus 1, the quantity squared. And you see what number we're getting over here? We're getting a 9. We're at the point that you should be able to take this and run with it. I encourage you to finish putting this in standard form and then see if you can analyze the rest of this conic section equation. Of course, we divided by 9. That was the step that I would expect that you did. And again, go ahead and finish analyzing this. This would be a good time to push pause. Next screen that you see is actually going to be the final answer. It's going to be all the numbers labeled on the ellipse. So go ahead and see if you can get everything that you need. Get A, get B, get C, get the center, and get your sketch. All right, how did you do? The one thing that sometimes students need to see is that this center is not at 0, 0, so it makes it a little trickier, but since your center is at 2, -1, you're going to have to make all of your adjustments off of those x and y values. For example, since your c value comes out to be 2√2, you would have to add 2√2 to come up with the value of this foci. And you can write that as the center 2 minus 2√2. That's fine. You can write it that way. The y value doesn't change. That'd be how I got, for example, that foci. And you'd have to do the same thing with your vertex, meaning you'd have to adjust it from that center point, and that means I'd have to take, since my a value is 3, I'd have to be adding or subtracting, in this case, from my x value. So 2 minus 3, again, that's the a value of your ellipse. That's going to end up giving us this center of -1. Of course, the y value doesn't change, and that would be your vertex. Let's look at one last concept with ellipses, eccentricity. Now, eccentricity is, you're going to find out, is a number that comes from comparing two distances. Simply the distance c, which is a foci distance, and the distance a, which is a distance from the center to the vertex on the major axis. Now, I just want you to kind of think with me for a moment. If you took these two these points, and say you take the foci and you sort of drag it out, as we talked at the beginning of the lesson, you would end up with an ellipse that is a lot more oval. But what's really happening is that your c value and your a value are getting closer to each other, right? They're becoming equal. And if you take your foci and you do the opposite, if you drag them towards the center, as we talked at the beginning of the lesson, now your shape is going to be much more circular. But what's really happening is your C value and your A value are becoming very different. They are unequal. And so this idea of comparing these numbers is known as eccentricity. And what I'd like you to do is, as it says, actually take a moment and read page 645. This would be a good time to pause the video and see if you can find a few facts, write them down, and I'll meet you back here in a few moments to wrap this up. All right, so a lot of times students will say that eccentricity is basically the idea of the ovalness, if we can use that like an adjective, the ovalness of an ellipse. In fact, it really is a number that describes that ovalness. It's a number that comes from a simple formula, C divided by A, taking those two values that we talked about in the front of the paper and just finding out how close they get either to 0 or how close they get to 1. And so let's talk about it getting close to 0. That would mean that, of course, your A value is getting very large, and if your A value is getting very large and your C value is getting small, then we're going to have something that is much more circular versus when E approaches, we could say, 1. That means that the two values are very similar, and of course that means that we're going to have a much more oval or ovular, I guess I'll maybe use the word elliptical, that might be a little better. It'll be more of an elliptical ellipse. So can we find the eccentricity of some of these examples? Sure. It's actually just as simple as dividing C and A. If we sort of throw this in as a little extra thinker for these, I could say that my E for this problem, back to this first one, C over A is going to be 2 over 3. Now 2 over 3 is a number that, of course, is between 0 and 1, but we could use that to compare with maybe this ellipse over here that had an E, or excuse me, a C value of 4 root 3 and a value of 8. Now, if you divide those numbers, you get 0.87. It's okay to change it to a decimal because sometimes that makes it a little easier to compare it. So we get 0.87, and of course 0.87 is a little bit bigger than 2/3, which means that we're going to end up with an ellipse that is more ovular, more elliptical than the other. How about one more? This guy at the bottom left corner, excuse me, the bottom right corner, where we had an C value of 2 root 2 and an A value of 3. That was going to, that as a decimal comes out to be 0.94. Again, it's good to write this as a decimal because you can see then that this ellipse that I guess I never drew, but that was shown on this diagram, is the most elliptical of all of them, as it is has the largest E value. And those of you that you may have studied elliptical orbits of our planets, you can see how each of them has a different eccentricity that's also described in your book there at the bottom of page 645. All right, you're ready to do your assignment. Same as the parabola assignment, you want to do it carefully, correctly, and keep in mind that the real reason you're doing it is to learn this concept, because next year in calculus, it won't be until you actually do your assignment that you start to really learn the material. But I am going to grade you on correctness, which is to encourage you to do it well, and you'll be able to upload that along with your ellipse mini check on the next day.